Let's work through an example of using the fundamental theorem of calculus to compute the line integral f dot dr over the curve C. Now in this case, because our vector field is rather complicated and our curve is particularly simple, the standard method to compute the integral of f dot dr over C is going to be pretty cumbersome. And it's not that it will be impossible, but it'll obviously be a lot of work. So instead, if the vector field f is conservative, so if I can write it as the gradient of some potential function, little f, then instead I can sort of ignore a lot of this complication and simply evaluate the potential function at the endpoints here, which is usually a considerably easier thing to do. All right, so let's see how this works. So we need f to be conservative, so that means we need this function to be the partial of little f with respect to x, this function to be the partial of little f with respect to y, and this function to be the partial of f with respect to z. Okay, now it's not always true that every vector field is conservative, but we'll see that in this case we do have a conservative vector field. So what should be our potential function, little f? Well, if I look this through, it looks complicated, but really it's just an application of the chain rule. So I have a function of x here, and if this is going to work out well, in the end I have negative sine of a function of x. So if I think about cosine of natural log of 1 plus xz, that's going to be involved in the antiderivative with respect to x of this function. Of course, I have the square root of y, but that's just constant with respect to x, so I don't have to worry about that too much. I just throw it on the end there. Now, what's the derivative of this with respect to x? Well, I get negative sine of natural log of 1 plus xz times root y, and then times the derivative of natural log of 1 plus xz. So that accounts for the rest of these terms. I get a 1 over 1 plus xz times the derivative of this with respect to x, which is equal to z. And so in fact, I see that if I had f of x, y, z is equal to this function, then the partial derivative with respect to x would be this first term right here. Now, we're not quite done yet, because there could be extra terms here that are just functions of y and z, and they would only show up in the second two terms. They wouldn't show up here because this is just the partial with respect to x, and if they're just functions of y and z, their partial with respect to x would be constant. So for instance, this 2yz shows up in this term. Now, the cosine of natural log of 1 plus xz over 2 root y, that is the partial derivative of this function with respect to y. This is all constant, and the derivative of square root of y is 1 over 2 square root of y. So this part is accounted for right here, but now we have this extra function of y and z, whose antiderivative with respect to y is y squared times z. So we sort of needed to add on this term, and there's no way we could have seen this term in the first component, because when I take the partial of this with respect to x, it would go to 0. Now, we've accounted for the first two terms. We have to look at the third term, and there could be an extra function of z here that wouldn't show up when I look in the first two terms. Now, this term, of course, comes from this term in f, and the y squared comes from our y squared z right here. And in fact, that's it. There's no extra terms. So in fact, this third term is just some constant whose derivative with respect to z would be 0. Now, of course, we can take any partial derivative we want, so I might as well take the case where the constant equals 0. So in the end, I've looking at cap f and doing a little bit of really single variable calculus a few times, I've concluded that little f could be cosine of natural log of 1 plus xz times root y plus y squared z. All right, and so that's the function we're going to use to evaluate the integral of f dot dr over c. So here we go. So we got the integral over c of f dot dr, and this is equal to f of, and then the parameterization r evaluated at the endpoints. So I have r of pi over 2, and then minus f of r of 0. And so now we see that we've done the hard work of finding the potential function, although it wasn't that hard. And then we can exploit that to really ignore most of the curve and just focus on the two endpoints. So what is r of pi over 2? Well, cosine of pi over 2 is 0, so I get 0 for the first term. Sine of pi over 2 is 1, so squared is 1. And then again, cosine of pi over 2 is 0, so I get f of 0, 1, 0 minus f of r of 0. So when I plug in 0 here, sine of 0 is 0, so I get 0 for the first coordinate, and again for the second coordinate, and cosine of 0 is 1. So I get f of 0, 0, 1. Okay, so now we're going to use our potential function. So I get cosine of natural log, and then now x times z is 0 times 0. So that's just equal to 1 plus 0, which is 1. And then times the square root of 1. And then minus, plus y squared z, but of course z equals 0, so I would technically get plus 0, and then minus f of 0, 0, 1. So now, because y equals 0, both this term and this term will be 0, so I get minus 0. Alright, so you sort of ignore these. So in the end, I just get cosine of natural log of 1. Natural log of 1 is 0, so I get cosine of 0, which is equal to 1. Okay, so in the end, even though the potential function was kind of complicated, because the curve at the endpoints, had integer valued coordinates, and in fact were both ones and zeros, this computation was really easy, even though the potential function is a little bit complicated. And it certainly was a lot better than trying to find r prime of t and looking at f of r of t. I'd have sine of natural log of 1 plus sine cosine times cosine times the square root of sine squared over this nonsense. I mean, it really would have been complicated to do this using the standard method, and don't take my word for it. Try to do it yourself and just see what the work would entail. It's a good lesson in sort of comparing different methods and seeing what they're good for. And in this case, applying the fundamental theorem of calculus and finding this potential function allowed us to get out of a lot of work and compute this line integral in a rather straightforward fashion.